Hi students, and welcome to this lecture which is based on calculating the area between the curves. Now if I ask you what's the area of a circle, definitely the answer would be pi r square. If I ask you what's the area of a square, then it would be a square, where a is the side of the square. And similarly, if I ask you how to find the area of a triangle, definitely you can use a hero's formula to calculate the area of any triangle. But now if I ask you how to find area between two curves, then how are you going to find that? Yes, for that we are going to use a tool of integration. But how? That's something we are going to study in this lecture. So let's start this lecture and understand how to find area between the curves. Our previous lecture was all based on study of definite integrals. So we have talked a lot about definite integrals in that chapter. And in that we also studied that the major application of definite integrals is to calculate the area between curves. Yes, in fact, the definite integrals helps us to calculate the area between the curves, and this is what we are going to study in this lecture. But before we move into studying area bounded by curves, it's very much important for us to be able to trace the curves from their equations. For example, we have the curve x cube plus y cube equal to a cube. Now, if you don't know how to trace this curve, then you won't be able to calculate the area. So the key point is, to find the area between the curves, it's important for us to know how to trace those curves. Now we have already talked about how to draw the graphs of functions in our chapter on functions. So let's just take a quick glance at curve tracing. The first is, if x is replaced by minus x and the equation remains the same, then it is symmetrical about the y-axis. So if x is replaced by minus x and the equation remains the same, then fx is an even function, and so we can say that the curve is symmetrical about the y-axis. For example, y equal to x squared. Here if we replace x by minus x, then the equation remains the same, and we know that the curve of y equal to x squared is symmetrical about the y-axis. The second is, if y is replaced by minus y and the equation remains the same, then it is symmetrical about the x-axis. So if y is replaced by minus y and the equation remains the same, then we can say that this curve is symmetrical about the x-axis. For example, the curve y square equal to 4ax. We know that this is a parabola and it is symmetrical about the x-axis. So if y is replaced by minus y and the equation remains the same, then we can say that it is symmetrical about the x-axis. The third is, if x and y are interchanged and the equation does not change, then it is symmetric about the line y equal to x. So if x and y are interchanged but the equation does not change, then we can say that the curve is symmetrical about the line y equal to x. The fourth is, put x equal to 0 to know the points where the curve intersects the y-axis. We know that whenever a curve intersects the y-axis, the x-coordinate is 0 at that point. So putting x equal to 0 helps us to know the points where the curve intersects the x-axis. Similarly, if we put y equal to 0, then we get the points where the curve intersects the x-axis. The sixth is, find dy by dx to know the points of maxima and minima. So at the points of maxima and minima, we know that dy by dx is equal to 0. So those points gives us the values of maxima and minima. The seventh is, check the behavior of the curve when x and y tend to plus minus infinity. So what we do is, we make x and y tend to plus minus infinity and check the behavior of fx. So this gives an idea whether the function also tends to infinity or it tends to 0 and vice versa. So it gives an idea of the behavior of the curve. Eighth is, check if the curve is periodic. Now what does periodic mean? Periodic means that the value of the function repeats itself after a fixed interval. This fixed interval is called as t, which is also known as the fundamental period of fx. The ninth is, try to find the intervals in which curve increases and decreases. These are some of the key points which you must take into consideration while drawing the curve, and these points very effectively help us to trace out the curve of any equation. Now let's try to see how we actually try to find out the area of curves. Now case 1 is, if fx is continuous in a comma b, then the area between the curve, the x-axis, the line x equal to a and the line x equal to b is a equal to modulus of integral of fx dx from a to b. if fx is less than equal to 0 or fx is greater or equal to 0. Now if we say that fx is greater or equal to 0 or fx is less than equal to 0, then the area between the curve, the x-axis, the line x equal to a and the line x equal to b is a equal to the modulus of integral of fx dx from a to b. So if we say that this is the curve y equal to f of x. Now this is the x-axis, this is the line x equal to a and this is the line x equal to b. Then we say that this is the desired area which is between the curve, the x-axis, the line x equal to a and the line x equal to b, and this area is equal to the modulus of integral of fx dx from a to b. Thus the value of this area is modulus of integral of fx dx from a to b. Here we see that fx is greater than 0 in this interval a to b. Now case number 2 is the area between the curve x equal to f of y axis and the line x equal to a and y equal to b is a equal to modulus of integral of f of y dy from a to b if f of y is greater or equal to 0 or f of y is less than equal to 0. So here the case is just reversed. We are expressing x as a function of y and we try to find the area between this curve, the y-axis, lines y equal to a and the line y equal to b, and this area is given by modulus of integral of f of y dy from a to b. Here we know that area is always positive, so this area would be the modulus of integral of f of y dy from a to b. Also here f of y is greater or equal to 0 or f of y is less than equal to 0. Let us say that this is the curve x equal to f of y. Here important thing to note is x is expressed as a function of y. This is the y-axis, this is the line y equal to a and this is the line y equal to b. Now the area between this curve, y-axis, the lines y equal to a and y equal to b is this portion. And the value of this area is modulus of integral of f of y dy from a to b. The case number 3 is if there are two functions fx and gx such that f of x is less than equal to g of x for x in the interval a to b. The area between these two curves and the line x equal to a and x equal to b is given by a equal to modulus of integral of gx minus fx from b to a or from a to b. Thus, if there are two functions fx and gx such that fx is less than equal to g of x, that is this function is less than gx for some interval a to b, then the area between fx gx, the lines x equal to a and the line x equal to b is given by a equal to modulus of integral of gx minus fx from b to a or from a to b. Thus we simply subtract these two functions fx minus gx or gx minus fx and we integrate them from a to b. So if we say that this is the curve g of x, this is the curve f of x, we see that g of x is greater than fx here. Now we have any point x equal to a and x equal to b. The area between g of x, f of x, x equal to a and x equal to b is this portion. This portion represents the area between the curves and the lines x equal to a and x equal to b. So this area is given by a equal to modulus of integral of g of x minus f of x dx from b to a. Now there are few more important points to remember. If a curve is completely above the x-axis, then we take it as positive, and if a curve is completely below the x-axis, then the area would be negative, but by convention we always take it as positive, so we apply a modulus sign over there. Now if I say that there's a curve y equal to fx that lies on both sides of the x-axis, so for some portions it is positive and for some portions it's negative. Let us say that this is the curve. We see that here it is negative, here it is positive again, here it is negative, and here it is positive again. So this value would be negative because this portion is below the x-axis, then is above the x-axis, and so its value would be positive. This portion is again below the x-axis, and so its value would be negative, and this portion is above the x-axis, so its value would be positive. By convention, we take area as positive. So we write A, that is the total area, this area plus this area plus this area plus this area, is equal to modulus of A1 plus modulus of A2 plus modulus of A3 plus modulus of A4. So the total area A is equal to the modulus of A1 plus modulus of A2 plus modulus of A3 plus modulus of A4. If the curve is symmetrical about the x-axis or the y-axis, then what we do is we calculate the area of the symmetrical part and multiply it by the number of symmetrical parts to get the whole area. Now we have discussed enough on how to find the areas between the curves. Let's start to apply this knowledge to solve problems. So this problem appeared in ITJ 1982 and it says that the area bounded by the curves y equal to fx, the x-axis, the ordinates x equal to 1 and x equal to b is b minus 1 into sine of 3b plus 4. Then fx is, option number A is x minus 1 into cos of 3x plus 4. Option number B is 8 times sine of 3x plus 4. Option number C is sine of 3x plus 4 plus 3 times x minus 1 into cos of 3x plus 4. And option number D is none of the above. So in this problem, we have been given the area between the curves y equal to fx, the x-axis, the ordinates x equal to 1 and x equal to b. And through that, we have to calculate fx. And we have been given the 4 options. So let's see how to solve this problem. We know that the area bounded by fx, x-axis, the ordinates x equal to 1 and x equal to b is given by a equal to integral of fx dx from 1 to b. Now we have also been given that this area is equal to b minus 1 into sine of 3b plus 4. Now what we do is we differentiate both sides with respect to b. Now we use the Leibniz rule to calculate the differentiation of any integral. So f of b would be equal to 3 times b minus 1 into cos of 3b plus 4 plus sine of 3b plus 4. Thus when we differentiate this equation, we get f of b equal to 3 times b minus 1 into cos of 3b plus 4 plus sine of 3b plus 4. Now this is expressed as a function of b. If we replace b by x, we get f of x equal to sine of 3x plus 4 plus 3 times x minus 1 into cos of 3x plus 4. And this is nothing but option number C. So option number C is correct. Let's see another problem. This problem appeared in ITJ 1991 and it says that sketch the curves and identify the region bounded by x equal to 1 by 2, x equal to 2, y equal to log x and y equal to 2 to the power of x. Now find the area of this region. So in this problem we have to do is we have to sketch the curves and then identify the region bounded by these curves, and then again we have to calculate the area of this region. So in this problem we have been given 4 curves, that is x equal to 1 by 2, x equal to 2, y equal to log x and y equal to 2 to the power of x. So we have to calculate the area bounded between this region. First step is we are going to sketch the curves. So this is the curve for y equal to 2 to the power of x. Now this is a very standard curve. Similarly, y equal to ln x is again a very standard curve. So this yellow curve represents the equation y equal to ln x. This is equal to 0 at x equal to 1, and when x tends to infinity, this also tends to infinity. Similarly, when x tends to 0, it tends to minus infinity. So this yellow curve represents y equal to ln of x. Now this is the line x equal to 1 by 2 and this is the line x equal to 2. So actually the area between these two curves and these two lines is this portion. This pink portion represents the area between the curves y equal to 2 to the power of x, y equal to ln x, x equal to 1 by 2 and x equal to 2. Now we have to calculate the area of this portion. So the area of this portion is equal to integral of 2 to the power of x minus log x. We know that this curve is greater than this curve. Let us say that this is gx, this is fx. Then the area is given by integral of gx minus fx from a to b. So area would be equal to integral of 2 to the power of x minus log x from 1 by 2 to 2. Now the integral of 2 to the power of x is 2 to the power of x divided by log 2. and the integral of this would be minus x log x plus x from 1 by 2 to 2. Thus when we put x equal to 2 and x equal to 1 by 2 and subtract them, we get the final value of this integral as 4 minus root 2 divided by log 2 minus 5 by 2 into log 2 plus 3 by 2. Hence the area between the curve y equal to 2 to the power of x, y equal to ln x, the lines x equal to 1 by 2 and the line x equal to 2 is equal to 4 minus root 2 divided by log 2 minus 5 by 2 into log 2 plus 3 by 2.